All right, like I said, I wanted to show you what this graph looks like, this x cubed over x squared plus 1. I zoomed in a little bit on my calculator just so that you could see it. And you can see it's a little bit hard to tell with those points of inflection, but you can see that like there's something weird happening at that line y is equal to x. There is no maxes or mins, but you can tell like maybe there's some concavity situations happening. If you were to use like a stronger software, you might be able to get a better picture of it. Let me zoom out just so that you guys can see what it would look like kind of originally. All right, that's kind of what it looks like on a standard 10 by 10 curve. And if we zoom in, like I said, that's what we get. And even if we zoom in a little bit more, I don't think we're going to get anything all that great. Yeah, our calculators just aren't strong enough. All right, but that's the idea. Okay, so 4.7 is optimization. So these are word problems, all right? These are like, I don't want to say fun, but they're kind of neat little problems, all right? Now, optimization talks about like maxes and mins and how to find the maximum of something or the minimum or something. Like this is what we're doing here, all right? So I'm going to actually jump around a little bit in this section, all right, because I think that some of them make more sense to do than like first than others. All right, so first off, like understand the problem, right? Steps in solving optimization problems. What's the unknown? What are the given quantities or conditions? Okay, first off, draw a picture. All right, pictures are important. We want to make sure that like something is accurate, right? And if we can, right? There may be a couple of scenarios where we can't, but let's draw a picture. Introduce notation and or domain, all right? Sometimes we may have a domain situation. Okay. Rewrite in terms of the max or the min equation and try to get it down to one variable. I know this doesn't mean a whole lot to you as it's written, all right? But when we do a problem, like this is all going to kind of follow step by step. And then use our methods to find absolute maxes or mins. Be sure to check the endpoints if you have a closed interval. Okay. That's pretty standard how we do it. Now this first example, this farmer example is pretty, like every calculus textbook in the world has this problem basically. All right, so a farmer has 2,400 feet of fencing, wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? So largest area tells me you want to maximize the area. So that's the formula that we're going to maximize, okay? So let's draw this picture. Okay, here's your river, right? And he's going to make this fence. We can kind of call the edges of the fence whatever we want, right? Let's call 2 x's and y's, right? We can name it whatever we want, but if it's a rectangle, these two lengths will be the same and we'll have this length y. We do not need to fence the riverside, okay? Now he says that we're going to have 2,400 feet of fencing. So that means I'm going to use 2,400 feet of fencing to create this barrier, this fence, right? So that tells me that 2x plus y is equal to 2,400. My perimeter is 2,400. We're going to assume he uses all of the fence. All right, we're in pretty good shape actually. So that gives us our perimeter, and we know that we want to maximize the area. All right, we know area of this rectangle would be x times y, length times width, right? X times y. So I'm going to end up wanting to take the derivative of this. If you want to maximize the area, we're going to take the derivative of the area. Here's the problem. We have two variables. And we're not messing around with like nothing, like we're not taking the derivative with two variables, right? That ain't it, okay? So what we're going to do is we're going to use this other equation that we formed and rewrite it so that we can get the area equation in terms of one variable. So there we go. Rewrite in terms of max or min equation, get it down to one variable. There's your step 4. So I'm going to call y and say y is the same thing as 2400 minus 2x. And we're going to do the substitution. So I'm going to say x times 2400 minus 2x. And I'm plugging it into the area problem or the area equation because area is the thing that I want to maximize, is the thing that I want to take the derivative of. So I'm going to plug in this extra information into the area equation because this is the equation that I want to maximize. They want to find the largest area. All right, so that's why we're not doing it like vice versa or anything like that. Maximize this equation. So we could use a product rule here if we wanted to. Or we can just distribute and then take the derivative. That might be a little bit easier, right? Minus 2x squared. So that's our area. So just a little couple of things here, like nothing outrageous. Like our lengths have to be bigger than 0. So just like as a heads up, we want to make sure that our distances are bigger than 0 when we do this problem. Okay. So let's take the derivative of the area, all right? So a prime, you hear my dog, a prime is going to be 2400, just by itself, 2400, minus 2x squared, so minus 4x. Like I said, we're maximizing, so we're going to find the first derivative, we're going to find critical numbers, and we're going to make sure that we get a maximum and plug in and see what we get. All right, so 2400 minus 4x. Set it equal to 0. We're going to have 2400 is equal to 4x. Divide by 4, x is equal to 600. My dog's upset because she left her treats underneath the couch. So let's make sure that we have a maximum here, okay? This is our only critical number, so I feel pretty good about it, but let's just check, right? It gets us in a good habit of checking in case, because there's going to be scenarios where we get multiple critical numbers. We want to make sure we get use the right one. So I'm going to say 0, and I'm going to say 0 because we're not going to have any negative lengths. So my interval is going to look like 0 to 600. And you could either say 600 to infinity or 600 to 2400. Like it kind of will work out the same way. I'm going to say it goes to infinity, but like it could only go really to 2400. But we're not going to encounter any other issues here. We're going to pick a test value in the interval from 0 to 600, whatever one you want. 1 is good. 601, and that second one works out fine as well. All right, so then the last step I want is the sign of the derivative. Sign of the derivative. Sign of the derivative, if I plug in 1, 2400 minus 4 times 1 will be positive. And if I plug in 601, this will be negative. All right, so we're going from increasing to decreasing. So yes, we have a maximum. So that's what we were checking, right? Making sure that we just had a maximum, that nothing outrageous or silly or anything like that happened. So at 600, we have a maximum. X is equal to 600. That's great, right? We are like almost done with this problem. So we have a maximum when x is equal to 600. They just want the dimensions of the river. So if x is equal to 600, y is equal to 2400 minus 2 times 600, 2400 minus 1200. Y is equal to 1200. So the dimensions that produce the largest area are 600 feet by 1200 feet. You have one in your homework very similar, okay? So this will happen a lot Well, we'll have two equations, right? You'll have to maximize one of them, and you'll do like a little substitution. And like I said, even if you only get one critical number here, like it probably is going to be your max or your min, depending on what you're trying to find. But we want to just make sure that that is what happens, right? We just want to make sure that we get into a good habit there. So we do a little mini first derivative test. It doesn't take us that long. And then once we feel good that that's what we have, we're going to plug in and get our dimensions.